because our final layer output is a pre-activation. So the function that we care about is going to be expressed as one of these z's. And if we do this integration, one of the things that's nice is by the central limit theorem, when we take infinite width, we're going to get a correlated Gaussian distribution for our functions. And then if we back off this limit, we get a nearly Gaussian distribution that we can correct perturbatively with an expansion parameter that's the ratio of depth to width. And so, but here, okay. So if we look at our pre-activations, the things that's nice about them, oops.
Right, if you click on it.
Okay. So nice thing about these things is, again, if we want to compute those moments that we're interested in, like the variance or the kurtosis here, we can do that just like we would in field theory. And again, when we take the limit as the width goes to infinity, we drop out non-Gaussian interactions and we get a Gaussian free field theory that we can worry about. So the last thing is when we look at the probability distribution for our functions, it's going to be expressed essentially as an exponentiated action. And we can think of all of our moments in the distribution as couplings in this action. And so these different couplings are going to be suppressed by powers of the width. And they're also going to have a dependence on the depth L up here. And the way you can think about that dependence is the couplings are going to evolve in a renormalization group flow with depth. And so one thing that we do is we choose specific values of our initialization variances to pretty much have this perturbative scheme in the ratio of depth to width so that we can analyze these things perturbatively and in an understandable way. So yeah, putting it all together, we can get this probability distribution. We can compute any correlations that we're interested in. And what this allows us to do is to think about the solutions to our neural networks as a Taylor expansion about initialization. And one of the claims that Robert's to make is that you only need up to 3 derivatives, and then you get this expansion that's really nice and nearly Gaussian. So in our first paper, we took these ideas and we wanted to try to validate them in a nuclear physics context. So we looked at binding energies again. And 4 of the big headlines were that our distributions were in fact nearly Gaussian, which is nice. The weights and biases also shift very slightly, so we can actually use this Taylor expansion in a valid way. We found different learning regimes that were predicted by neural network field theory. We'll talk about this a little bit more with examples in a second. But finally, what we found is that when we tuned things to criticality, when we chose those specific initialization weights and scaled learning rates in particular ways to ensure that we have this expansion in R for our probability distribution, our networks outperformed the stock stochastic gradient descent trained neural networks for binding energy performance. So again, to look at our distributions, what we did is we just took neural network, initialized it a bunch of times. And when we had a width of 1, this is not a very Gaussian distribution. But as we increase the width, it becomes more and more Gaussian. And this works not just for the relo activation function, but all activation functions that we tried. These Gaussians are also correlated, and we can compute the covariance kernel for it. Oh, my bad. We can compute the covariance kernel between all of our different inputs here. And you can see that for inputs that are across the origin from each other, they're non-correlated here, and then very strongly correlated over here. This is for a network with 1 hidden layer. And so if we take it to have more, we can see that this actually introduces correlations. And so the kind of intuition about ratio of depth to width being our expansion parameter is depth introduces correlation, width averages them out. And so you want to have a small one so that you have minimal complexity, but enough complexity to actually have feature learning and properties that are important to neural networks. So second claim, what we did was we took the initial weight matrices, initial bias matrices, then we trained an ensemble of networks and we got their final weights and biases, and we took the Frobenius norm of their difference. And in the regime that we care about, where we have that small r, the difference was about 10 to the minus 2. That's our largest contribution to the Taylor series. Anything higher than that is going to be much, much smaller. So that gives us some validity to using this Taylor series to look at our solutions and their distributions. And then we looked at different regimes of learning. So on this right side here, we have basically plots of binding energies, residuals that we learned. And over here, This is a plot of the root mean square deviation with experiment with our binding energy networks at various values of the ratio of depth to width. So in this first regime here, we had a width of 1,000, which is pretty large. And you can see over here that our root mean square deviation jumps up, but we're still fitting. So what's happening is neuron correlations are being turned off. All of the non-Gaussian interactions in our action are being suppressed. And so we are able to fit things still, but we're losing the ability to do feature learning. And if we take the limit as R goes to 0, then we're just going to get back a Gaussian process and can fit, but it's not going to be able to find features in the data. If we go down to this kind of central pit here, you can see that the networks get a little darker. It means that they're getting better residuals and there's actual feature learning happening. And we can see that there's also an optimal ratio of depth to width, which is a nice thing to see as well. And then finally, as we start to move from this valley and increase and approach towards 1 or greater, we're starting to lose any features or performance here because the networks are becoming overly correlated. And so the correlations between neurons are too strong to learn any features, and our analysis becomes non-perturbative. We can't just chuck out any of the higher order moments that are normally suppressed by powers of the width. So that's interesting. It gives us a prescription to build ideal networks in this case. So the last thing that we did was we built a bunch of different networks to compare. They basically used critical prescription. So what that means is we chose very specific values of the initialization and scaled learning rates for the weights and biases in a particular way so that our training is stable and we can perform this type of field theory analysis. And we did 3 different combinations. We either did a fully critical network that has both of these prescriptions, half critical, which just used the initialization, and then a stock SGD optimizer, it's stochastic gradient descent, or a just out-of-the-box SGD PyTorch network. So we looked at the loss as an error metric, and what we can see is the fully critical network in blue gets a much better final loss value than any of these other guys do until we get to greater depths when the half-critical network can start to compete. But networks without any criticality tend to stagnate and don't perform as well as these other guys by several orders of magnitude. This is for Arelu. If we do it again for Tanch, we see similar behavior. The fully critical network beats out the other 2. The half critical gets better over time, and then we get stagnation in the non-critical network as we increase the depth. It's another error metric. We computed the root mean square deviation for the binding energy again. And once again, we see that the fully critical network gets the best value at 1.89 MeV. So this is nice. But in practice, most people are using atom optimizers, which are an adaptive gradient descent optimizer. And if we train an ensemble of networks with atom, where both critical and non-critical initialization, it outperforms the fully critical network from before. So this is the current challenge that we're interested in is we have outperformed the stock SGD optimizers, but atom is still winning. And we have the advantage with critical networks that we can do field theory on them and understand what's going on, but we're still being outperformed by the state of the art in this case. So what we want to try to do is find ways to modify these critical networks where we can still apply a field theory analysis, but we also want to introduce these new behaviors and try to describe them through the field theory picture as well, so that we can have something that's competitive and understandable. So the first thing that we tried to do is we looked at what's called mini batch training, which is where you take your training data set that you're learning on and you cut it up into little batches of batch size B. And essentially what happens is it performs multiple gradient step updates during the gradient descent and tries to work its way towards a minimum. And what we can see is when we look at the root mean square deviation for the binding energy here, I think the laser's dead. Oh, well. So what we can see here, though, is the blue network, which is the fully critical, and the other ones, which are the atom networks. At a large batch size with full batch, we get that the critical network is being outperformed by the stock atom network. But as we decrease the batch size, the critical network continues to improve, whereas about batch size of 8, the atom optimizers start to perform worse. Oh, thank you. Great. So this is nice because it means we have found an empirical way to outdo an atom optimizer with our critical networks. And so we want to try to understand mini batching, and then try to figure out how to fit it into our field theory picture. So we like mini batching because it makes it so that our gradient updates, when we're trying to do gradient descent, have more noise. Sounds counterintuitive, but in full batch training, you're computing one gradient for each time step when you're trying to do gradient descent. And this gives you a deterministic trajectory towards a minima. When you do mini batching, though, you're computing multiple gradient steps for each batch. So you're doing multiple steps per time step. And if you think about summing up all of these for each time step, it makes it so that you have a noisy trajectory that's non-deterministic, and you can find other potential minima that work better, like we saw in the previous slide. So that's one reason why we like it. The others are it only affects our gradients in training. We can leave our initialization alone and not have to mess with any of the criticality we instilled there. And it only introduces one new hyperparameter to consider when we're trying to figure out how to set these things up. So how does the batch size appear in neural network field theory? Well, what we're going to have to do is look at our training dynamics and look at a quantity called the neural tangent kernel. So the neural tangent kernel is a quantity that talks about how neural networks evolve during training. And the elements of the neural tangent kernel basically represent correlations between function gradients when you're training these things. And so it's central to neural network field theory because when we think about our Taylor expansion, all of the gradients in that Taylor expansion are determined by the neural tangent kernel. So over here we have a graph where it's basically just doing regression through the NTK and finding a solution from this rather than, and then comparing it to like an ensemble of networks here. And that looks very similar to our Gaussian process picture from before when we update according to a posterior. So what's the relationship there? Well, in the infinite width limit, we get neural networks that act like Gaussian processes. The difference being, though, GPs are trained in one update step, whereas neural networks are iteratively done by gradient descent. So we have update equations for both the GP on the bottom and then the neural tangent kernel on the top. And in the limit, as the time steps go to infinity, they basically end up looking like the same equation and end up finding pretty much the same solution. So the way that you can think about this in the field theory POV is you're adding a source to your action, and the GP will do it in one step and add that correction there to account for how it responds to introducing data. Whereas the NTK is going to do a time-dependent source that gradually introduces this and looks at the response to data being introduced. So the neural tangent kernel at infinite width is frozen. It remains constant, and we don't get any feature learning. But when we go to set up the time evolution equation for our neural network to see how it evolves in time, it's a first order Diffie-Q. And for specific choices of neural network properties, it looks exactly like the imaginary time Schrodinger equation. So we can solve that. And the thing about the NTK then is it resembles a Hamiltonian. If we think about the infinite width solution then as like our free Hamiltonian, then we can introduce corrections in 1 over the width. And then we can find our probability distribution that we're looking for our neural networks. And so if we have an understanding of how to solve these equations, we can introduce new empirical behavior that we saw if we know how to describe it like we do with mini batching, and then try to introduce new things, see how they look in the theory, and then see how we can inform them the same way we do with other hyperparameters that we've determined, like that ratio of depth to width or any other kind of scaling. So currently, I am working to build a code that computes all of the 1 over n corrections to the NTK, and that should be done pretty soon. And once we have that, the idea is to look at mini batching and incorporating it. So the stock NTK formalism doesn't know anything about mini batching. And so an approach that people have been taking, Kumar and collaborators over at University of Washington, is they introduce the stochastic NTK, where they look at the time evolution equation and they introduce a noise contribution so that it matches like the noise introduced to gradients by mini batching. And so the NTK agrees pretty well with empirical results. From their paper that they put out, they have a wide network of like 1,024 with 3 hidden layers, and they use a batch size of 8. So this is their result from an empirical ensemble. This is the traditional NTK that doesn't know anything about mini batching. It does pretty terribly in finding a boundary between the 2 moons data set. And then the stochastic NTK does a pretty good job at finding that boundary. So that's nice. The current idea is to take what they've done there and try to generalize it so it can be applied in the field theory context. And then once we have that, we can solve it and see how well it models our situation. And then we can see about including more empirical results that improve network performance in an ab initio sort of way. And this will be the outcome. The outcome of this study is going to be what we publish as the next paper. And so just to give an outlook on where we're at, we understand the probability distribution properties pretty well. And now we're looking to study our posterior distribution. We're going to look at the NTK and look at those time evolution equations and try to introduce new successful phenomenology in an ab initio way, and then continue to build analogies between many-body physics, GPs, and ANNs. And our kind of wish list is to imply more many-body methods to neural network field theory. So doing like an HS transformation on things, looking at Pranav Sharma's variational perturbation theory approach. I'm going to try to engineer some new activation functions and kernels based on our understanding of the relationship between the two. Look into getting some ANFT results for adaptive optimizers, and then, of course, most importantly, applying these to more nuclear physics problems. Thank you.
Thank you, Simon. That was really fascinating. Lots of interesting things.
Yeah.
So there must be questions. Dos.
One of your earlier slides,
Yes.
you find this minimum at R equal to 0.4. So
Yes.
I was just wondering about that. It is right.
Mhm.
So two questions. So is it clear why that is a good number if one from the outset? Or-
Yes. So that number, that R star there, is actually determined through an information theory argument. And in the original text that Robert and Yaida put out, they basically make an argument through like mutual information between different parts of a neural network to compute that R star value to third order in R. For context, all of the calculations of like observables and things that we're doing is to first order. So we're very confident that that value works. And this is us seeing that, lo and behold, it does appear when we do this type of realization.
And then maybe related, so the error bars go up because you do perturbation theory. Is that correct? Or-
Yeah, so it's twofold. And I'm hiding a little bit of the information, but we discuss it in the paper. But yes, the error bars start to increase because we're doing perturbation theory and we're moving into the non-perturbative regime as we go up further. And then this wide bar here, I mentioned it here, but what ends up happening is you basically have it transitioning from the effectively deep regime where it can learn into this non-perturbative regime where it just tries to find anything that satisfies a loss minima. And so your probability distribution for your outputs ends up becoming either somewhere, around 3 MeV like we had before, or it just finds whatever gives this guy here and gives you a distribution that's centered at like 72 MeV because it tries its best to learn this and it finds a minima for this given loss function. We're using mean absolute error, but it can't actually do it because the neurons are too correlated in the theory. And so once you enter that non-perturbative regime, it really loses its ability to do anything.
Thank you.
On the same page, this is just also one way to think about it is underdetermined versus overdetermined in terms of number of parameters you have, because we have width equals 4, there's few parameters to learn anyway.
Yeah.
You're overfitting probably.
Yeah, I think that I would have to look at, there's an argument that's made about sparsity in terms of like, the number of parameters that are determining your distribution. And there's a handful of literature on this. I'd have to read it to make sure that I'm not making things up, but that sounds like it matches the intuition that I have from reading those things. So I think that would be a good way to think about it, but I can point you in the direction of some papers that might give you a more specific answer.
Good questions?
Time for quick comment.
Thank you.
I really like the book. I think I understand that you were more interested in understanding what happens to the network in reproducing the data as you play with discretity.
Mhm.
Based on the discussions we were having a couple of days ago about lies, I think you were in the room when
I was in the ODE room because I had questions about my
I see.
equation. So if you want to talk about that more, or if you have a brief summary. Yeah.
I complained so much about doing explicitly that because that was my project as a grad student.
Yeah.
So I did it terribly, much
Yeah.
less than you. But one of the things that I was complaining is that the networks that I trained had very poor extrapolative power.
Yes.
Have you played with, instead of feeding experimental data, feeding, let's say, the data of a model and between two models, and then try to extrapolate and see if the network on top of this performance inside is learning something useful outside?
I've not tried that, but
Okay.
I'd be willing to.
Sure.
Sounds like fun.
We can talk more later.
Great. Sounds good to me.
So Simon, I actually had a question. So
Yeah.
would it be correct to make the analogy that you're thinking of the neural network as a Euclidean time lattice field theory? That we're propagating with Euclidean time. As you go further, you get more and more correlations, you get some sort of correlated state, sort of the target. And then in that sense, if I think of it as a Euclidean time lattice field theory, the question I have is the role of the connectivity from one time step to the next, from one layer to the next, right? So if you do all to all, that would be like a field theory where you have hopping for particles from here to the moon.
Yeah.
Right. But if you made it local, then the properties would change a lot. So my question is about connectivity. If you restricted the connectivity to like d-dimensional connectivity for your neural network, could you have sort of more field theory, like properties that would have dimensionality, sort of criticality dimensions and stuff like that?
So yes, I have to, a lot of this is going to be stuff that we're going to look into as we get more and more many body approaches. But yes, there is like critical dimensions and things like that pop up. And there's actually some work on that in the latter chapters of Robert Snape's book. I think chapter 9 may start to introduce some of these ideas. They don't go as far as saying, all right, we're going to, look at this lattice explicitly and apply these constraints, but they say, all right, for the system that we have set up, here's how you can think about critical dimensions and behavior like that. So
Okay.
stuff exists, and we're just going to have to push it further and see what happens. So
Okay. Very nice. Other questions, comments? Okay, let's thank Simon once again.
So before we start, just wanted to apologize that I was talking with Thomas that this time step that you spent a lot of time. We didn't know that. I didn't know you were having this issue. So
So talk me on.
Okay, yeah. Yeah, so I apologize that I didn't know that you guys had this issue.
And see the shadow is this. Okay, I think it should be working. Let me say. So
Might as well get started a little bit early. Why not?
Okay, our next speaker is Maxwell Rothman, and he's from UTK, University of Tennessee. He'll talk about new lattice ab initio computations of atomic nuclei on lattices. Go.
So, like you just heard, that's the title of my talk. It's so maybe a brief overview of what I'm going to cover is an intro to new lattice, this Python program that we developed. Just some brief description about how the interaction that we published doesn't find alpha particles, so we need some better interactions. And we took these interactions from the nleft operation for just the simple ones with only 2 nucleon forces. Don't seem accurate, but it seems like we can't do 3 nucleon forces because they just take up so much room. So we need to optimize a new interaction, and this leads us to needing emulators for that. So new this is a set of Python programs that, like I said, performs computations on atomic nuclei on a lattice with periodic boundary conditions. And for a periodic cube with L sites, it can do full configuration for A equals 2, 3, 4, for L is less than or equal to 4, do Hartree-Fock with large L's, no problem. And then it has coupled cluster with singles and doubles. This requires L is less than about 6, and it has ISMRG2 requiring L so less than or equal to 3. So why would we want to work on LAS instead of our traditional harmonic oscillator basis? It's really to save on the storage. So the three-body matrix terms on a harmonic oscillator basis quickly goes to terabytes of data, and that's just unfeasible to work with. So you can see the different scalings here that one body term scales like L cubed, two body L to the ninth, three body L to the 15th. On the other hand, everything is very sparse, so all three of these scale like L cubed. So the first interaction we published and we took a look at was a simple contact interaction from finalist effective field theory, and the kinetic energy is just the leading order approximation of the velocity, and you can see that here. And so we also need to take advantage of this sparsity and not store a bunch of zeros. So essentially, we store lists of indexes and values instead of the whole thing, and then work with that in order to save this space. And then because of this, we could also use symmetry to only store ordered states with, say, for the two body, P is less than Q and R is less than S. And so we can see some results from the FCI code, and that it's mostly here to benchmark the other codes because it can't run on large lattices or large A's. And it computes the matrices for the kinetic two body and three body interaction, so stores them as compressed sparse row matrices, and then the lowest few eigenvalues are then computed. The Hartree-Fock starts with a one body density and then computes the tensor contractions with the two body and three body operators. This takes advantage of the sparsity better than the FCI. And you can see that we can run something like this loop that only bothers to check over the non-zeros and doesn't waste time moving through many zeros in the sparse operators. The coupled cluster code, maybe a brief description of coupled cluster, that the goal is to calculate the similarity transformed Hamiltonian, then solve for these TAIs and TABIJs recursively until the calculation converges. And then this is a little slow, so we accelerate it using this DIS method. And so we have two different types of contractions here, some that are between two dense objects and some that are between a sparse and a dense object. So one of these dense times dense contractions looks like this, and then this can just be done with a simple einsum. But then if we have a sparse dense contraction, because storing the intermediate tensors are too large, we loop over the non-zeros. And this trades a small amount of time for a lot of memory. And so maybe a look at the memory scaling for the couple cluster with singles and doubles is for oxygen 16. We can see that the memory scales like L to the 6. And this is because this TABIJ scales on the order of L to the 6. We can't store it sparsely because that would require adding sparse times sparse contractions, and those would cost a lot more time than it's worth in memory savings. And then the DIS itself takes a lot of memory because it stores effectively 10 copies of this TABIJ and the relative error between previous steps. And so that's effectively 20 copies of this, which, like I said, scales like L to the 6. And then this is an expected result that we see here, that we just get multiples of that. We don't bind alphas here, that you can see here with the energies of the different alpha clusters. And then we have singles co- uh, contributing a large amount of the energy for this coupled cluster. And so next, you obviously need better interactions. So instead of just a purely on-site one, we have one that has local and non-local spearing, taken from MLeft, and namely, we started with these two papers from 2016 and 2017, and we ran Hartree-Fock with them, and we saw that the energies really dropped down very low, which was not what we were hoping for. So we tested some nuclear matter results from them, and we see that even though the empirical saturation is here, the one interaction saturates much later, and the other one doesn't really seem to saturate. And then we were able to verify these results by analytically getting a result for a fully filled lattice, and we were able to get the same endpoints as the Hartree-Fock. So the solution to this would be to add a three-body term, and again, this was already done by NLEF, so we were hoping just to take their interaction, and we can see that for just the two interactions we looked at before, the scaling is quite large. It's still with L cubed, but we're talking about, for the more complicated interaction, a prefactor of 60,000. But for the three-body interaction, I couldn't fit it on this chart because it would be almost entirely above it. The prefactor is around 10 to the 7, so it's much larger. And so this is around 1.8 gigabytes per lattice site for the three-body term. And so that's not feasible to store ourselves or do calculations with. We can store a single site and say something about single sites, and we use that to get nuclear matter results as well. And we can see that unlike with just the 2 nucleon force, the 3 nucleon force seems to saturate close to the empirical saturation. And again, we were able to get analytical results for this endpoint, and it matches what we expected. So this kind of brings us to emulators in the future. And so at this point, we want to try and create our own interactions and optimize them, but we can't test it thoroughly if it's going to take 1.8 gigabytes per lattice site. So this is where emulators can help. So we're going to try and utilize them to optimize the Hamiltonians without having to fully realize it, which, as I showed, was problematic. And then the goal of NewLast was to really run on a laptop. And so these emulators can help keep NewLast running on laptops without giving up complexity that require a large storage cost.
Very, very nice. Nice progress, nice results. But there must be questions.
Yeah, very nice progress. So I'm wondering about the storage of the metric element instead of the SO3, which in the selenium, the symmetry we have the cubic symmetry, right?
Mhm.
So do you see any advantage if you take that kind of symmetry? Do you think that can reduce some of your storage to
Yeah, so we're looking into it. The problem is, it looks to be very complicated to on the fly realize this symmetry. It's possible, and then we would need only the 1.8 gigabytes for the single site and then just translate it as we move around. But that seems, it's something we're considering, but seems quite difficult to do.
Yeah, on the prior slide, first of all, interesting, really interesting thought. On the prior slide, you're talking about only storing a single site, and this seems to alleviate things and introduce the saturation. Can you elaborate, please? I'm not quite sure how that's going on.
So we can scale. So what we can effectively get this is only talking about nuclear matter and we can't get like any other results from this, but if we scale the interaction by the number of different points in the lattices, we're going to get the correct numbers here, but we can't do calculations with that.
Okay, gotcha.
Okay.
So since we're sitting on it, can you comment on what is driving saturation here?
So effectively, because there is a finite lattice spacing, it can't get any closer than like 4 particles on each lattice site, and now there's kind of like a forced gap that it can't get any closer than, because this is fixed lattice spacing.
And so this is kinetic energy then that's taking over?
Yeah, so effectively there's only so strong the 2-body and 3-body forces can affect it if it can't push it any closer, and so the kinetic energy wins out.
Questions? So maybe Maxwell, maybe we can actually help you out and do some calculations that are more convenient for the 3-body. Is just having fewer terms, is that exactly what you need?
And non-local smearing introduces, so local smearing is fantastic.
Okay.
As soon as there's a 3-body non-local smearing, we're talking gigabytes per lattice size and.
Oh, okay.
Well, so the problem isn't having non-local, the problem is having both at the local and not local. So if you have just one, it's around
So
50 per site, and then it's not 50 cubed per site.
if we had just local smearing with, let's say, nearest neighbor or next to near. Okay, because that's very easy for us to do that. It's just a choice. Yeah, and so, okay. And then you would have benchmarks that and we take the time lattice spacing very small so you wouldn't have to bother with that. That's fine. Okay, other questions? Okay, if not, let's thanks Maxwell once again. Okay, so we'll have a long coffee break, so we will resume on the schedule, which is at 11 o'clock. So use the time to discuss, to think about Streamline 3, to think about whatever has been presented here. Oh, so the goodies may not show up until 10:30 though, because that's the original schedule is good.
Oh, Thomas is good. Oh, I think it is. Try.